Okay, so I am a research fellow at the Dublin Institute of Advanced Studies working with Peter Keller. My main research area of focus is in solar radio physics, so I use large radio telescopes such as LOFAR to look at eruptive energetic activity on the sun. This talk will concentrate a little bit on general LOFAR science as well for the sun, and then I'll focus more on how we use the Irish LOFAR station in single mode, particularly as a platform for doing deep learning and machine learning. So as an overview, I'll just talk about the kind of phenomena we're really interested in, solar eruptive phenomena, radio observations of particles and shocks on the sun. I'll talk about why LOFAR observations are particularly good to study this eruptive activity. And then I'll talk about I-LOFAR in single mode, our high-performance computing facilities, and then a little bit about deep learning and neural networks with the Irish LOFAR station. So what are we interested in? So my research area of focus is in solar eruptive events, or coronal mass ejections. These are huge eruptions of plasma and magnetic field from low in the solar corona out into the heliosphere. They have 10 to the 25 joules of energy, travel at thousands of kilometers per second into the solar system. Most often observed in this green shaded region here called the coronagraph invisible light. The origin of them is observed in the EUV down low in the corona, but at the same time, when you get one of these eruptions, you also get a lot of radioactivity going on. So usually we observe this radioactivity in the form of a dynamic spectra of frequency versus time over here. And two of the most common types of radio bursts that are in association with this eruptive activity are type 2s and 3s. Basically type 2s are these guys over here. They last for about 10 minutes. Drift from high frequencies down to low frequencies over time. Type 2s are these much more impulsive vertical strips in your dynamic spectra, lasting a few seconds. This radioactivity has fluxes of up to 10 to the 9 Janskis, which terrifies most radio astronomers, because most radio astronomers are used to milli, micro Janskis. The sun is absolutely one of the brightest radio sources in the sky, and it's just a different ball game in terms of fluxes that we observe. What causes these things? So the modern paradigm for one of these eruptions is that we have a flux rope, a twisted ensemble of magnetic field erupts into the solar system. As it does so, it drives a shock on these open field lines. Shocks in plasmas are remarkably good at accelerating high energy particles, amongst which the electrons can produce what's called this type 2 emission over here. So not much time to go into detail, but type 2s are usually a signature of the plasma physics going on in a shock wave driven into the corona. At the same time, what you often get is particle acceleration on open field lines out into the solar system. Electron beams then emit the radio, and you get these type 3s over here. So radio in particular for the sun is a remarkably good way of looking at high energy particle acceleration in the solar atmosphere and the plasma physics associated with shock waves coming through the solar atmosphere. And I'll show a little bit more detail about why LOFAR is particularly good at observing these kind of phenomena. But why do we care? What is the reason why we want to study these phenomena? Well, we want to understand how the sun's atmosphere works in terms of the sun as a star, the fundamental plasma physics that we can get at by studying the sun in the radio domain, but there is much more of a practical impact at the same time. When one of these eruptive events occurs off of the sun, it can travel towards the Earth alongside its energetic particles. If it impacts the Earth, it can impact Earth's technological infrastructure in a variety of adverse ways. There's so many different ways that these things can have damaging impacts. So they can cause radiation hazards for astronauts on the International Space Station. They can even cause radiation hazards for the crew of transpolar flights, going back and forth between New York and Tokyo, for example. It can cause the ionosphere to become disturbed, and that can impact radio communication that depends on the ionosphere. One of the biggest effects are in oil and gas pipelines over here, or in electrical power grid systems. So activity on the sun can really bring down electrical power grid systems across large land masses on the Earth, and it can do so for hours. So in general, because of all of this technological impact, there's a need to be able to predict when the sun is going to erupt and forecast when it's going to arrive and if there will be some impact which could cause damage financially as well. As I've shown, because the sun is so bright in the radio, you may have guessed that one of the best ways to study space weather activity from the sun to the Earth is using LOFAR. And we've heard what LOFAR is. It's an international radio telescope spanning right the way across Europe, acting between 10 and 240 megahertz, and it's regularly used to observe space weather science. And the kind of science that you come across is that occurring on the surface of the sun, right the way through to the heliosphere, and down at the Earth into the ionosphere. At the moment, it doesn't observe the sun routinely, but there's a new project that Carley talked about in her talk, LOFAR for Space Weather, which aims to upgrade the entire LOFAR system such that it observes all of these phenomena routinely from the sun to the Earth, day in, day out, in order to provide forecasts of the entire system. And you can find a little bit more about that on the website lofarforspaceweather.eu. But in terms of observations of what LOFAR actually observes on the sun, why is it so good? Well, in my view, LOFAR has really unprecedented time and frequency resolution in observing erupted phenomena on the sun. So good that we can actually image individual particle acceleration events that was never available before. So this is a dynamic spectra like I showed before with frequency versus time here. This is a type 2 radio burst, so physics associated with a shock. So LOFAR's resolution is so good, we can see individual particle beam acceleration events occurring over time. So if you can make out each one of these stria here called herringbones, these are individual electron beams being accelerated. And just this year, for the first time, we actually managed to image where these electron beams occur in association with eruptive activity and shock waves on the sun. The observations were so good, we were able to use this to drive data-driven models. What we were able to do, particularly in this study, was model the magnetic field, the alpha-in environment of the corona, which determines how strong your shock is, and also project in 3D space where these particles are being accelerated. And knowing where they're accelerated is really important for how they'll propagate into interplanetary space and if they will arrive at Earth or not. So this is due to pretty much its remarkable time resolution. So LOFAR can get you down to milli, if not microseconds in its time resolution. It also has really excellent frequency resolution in the imaging domain as well, and the dynamic spectra and imaging domain. So this is from Contar et al. Edge Communications in 2018, where he imaged a type 3 radio burst, which had been done before, but with such fine frequency resolution, we can see that when we zoom into this type 3 radio burst, it's pretty modulated. It's not smooth, it's not clean. There are a lot of what he calls stria in the burst. Now these intensity fluctuations are directly related to density fluctuations in the solar corona. And when you plot up a paraspectral density of these density fluctuations, the power law comes out as -5/3. Now all the physicists in the audience will know this is a special number. This is an indicator of turbulence in the solar corona. So LOFAR, because of its really amazing frequency resolution, is one of the few ways to get at turbulent structure in the corona, which is to do with heating in the corona and the coronal heating problem. So these are just some examples of its remarkable frequency and time resolution, what you can observe, and the kind of physics it affords you to get at, basically. So that's LOFAR basically as an international telescope. But we can use these things in single station mode as well. And you can use them in high frequency and time resolution at the same time. So this is the Irish LOFAR station, and Peter showed some of this. So this is our station up in Birr, some of our equipment on the back end here, and this is our high-performance computing cluster that we've recently built on the back end of LOFAR. It's called the Real-Time Transient Acquisition Cluster, which is RAILTA, which is Irish for star, which Peter named, which is a really neat acronym. It records up to 488 frequencies, each at 5 microsecond time sampling. And that is about 4 terabytes per hour, which is a humongous amount of data to have to deal with on the fly and process on the fly. So what do we actually observe when we point LOFAR at the sun with a single station? This is what we observe. So Again, in our frequency time domain, we have radio bursts all day, every day. There are hundreds, if not thousands of them. So there's a huge variety of physics that we hope to glean from this. And the question is, can we detect all of these automatically? Because you don't want to go in and label every single one of these. It would take you or a PhD student their whole career to do so. So you want an automatic detection routine to be able to pick out these radio bursts, particularly to identify when the data is good, save it. If there's nothing there, just dump the data because there's so much of it. So there have been automatic detection routines before with some success, maybe 70 or 80% success. But we thought, why not use the modern trend in machine learning, particularly in deep learning and neural networks, to be able to automatically identify features in dynamic spectra. Now, for those who don't know, machine learning, it sounds pretty fancy, but it's nothing more than giving a computer tens of thousands of examples of something, an image of a radio burst, such that when you give it the next example, it's able to identify with good probability that it's a radio burst. So in particular, neural networks, they're basically inspired by the architecture of the human brain. We have a bunch of neurons, each connected to each other. Each of those neurons is controlled by a couple of parameters, W and U, you can see up there. Now, depending on the parameters, when we input an image, those W and U will give you probabilities of particular types of radio bursts at the back end of the neural network. What we then do is basically feed it more examples. Using mathematical optimization, we change the parameters of the network such that the probability of whatever burst it thinks it is gets better and better, until we reach something like it's 85% sure it's looking at a type 2 radio burst, which it is. Now, unlike this example where we have just 3 images, what you usually have to do is give it thousands, if not tens of thousands. Some of the biggest networks in the world require millions of images. So we decided to test whether or not neural networks have the ability to recognize solar radio bursts in our I-LOFAR spectrograms. And this is the results of some of the analysis that we've done. We used a neural network called Inception, which was actually built by Google to recognize images of everyday objects, cats, dogs, cars, and repurposed this with a method known as transfer learning to recognize solar radio bursts. So we have, again, I'll show us a movie here of our dynamic spectrum, frequency, time, and a time series of what radio burst the neural network thinks is in the image. At the moment, in this freeze here, it thinks it's a type 3 with 73% confidence, which there are type 3s in the frame. So I'll just play this, and it performs pretty well. So for the most part, it's able to detect what kind of radio burst is in the frame. Gets it wrong a few times, but that's to be expected. It's not always 100% confident. And I think a type 2 will come in now in a second, and you'll see the type 2 probability shoot up when it has an extreme level of confidence that there's a type 2 in the frame. So it's able to recognize the difference between type 2 and 3 radio bursts. A bit of confusion afterwards because both radio bursts are in the frame. And then eventually, which is an important point later on, when there's no radio bursts, it knows there's nothing there. So you're able to throw away data when it's not really useful. So you may have noticed as well that this just gives probability for the burst in the entire frame. It doesn't tell you where it is. What we want to be able to do is basically pick out where in the dynamic spectrum this radio burst is, so that we can analyze it even further. So we need to implement even more sophisticated neural networks. Now, there are a lot of networks on the market these days, pre-built, and that you can retrain using transfer learning. One of the best is called You Only Look Once, or YOLO. It's the fastest one of the fastest object detection and classification neural networks today. And it's basically used for everyday purposes. So if you have a picture of an everyday scene, it's able to recognize dogs, bikes, cars. We wondered, can we repurpose this network to be able to recognize the variety of type 2 and type 3 radio bursts out there? Now the problem is, this network is huge. It requires tens of thousands of examples of your radio bursts. We don't have tens of thousands of examples, so we have to simulate them. So what we've done is basically simulate 50,000 examples of a particular kind of radio burst we're interested in, supply the simulations to the neural network. It was trained on a nice GPU, and then once it's trained, apply it to our I-LOFAR data. Now, we applied it to this kind of data here, again, our dynamic spectrum, and there's some radio bursts where you can pick out that would be pretty easy to identify. Others will be remarkably difficult to identify. Even a trained human may miss some of the more blurred or less intense radio bursts, but to our surprise, it actually performs really remarkably well. So it's able to pick out the obvious ones as well as these really, really faint ones here, and importantly, ignore RFI as well. I think I have a movie here as well, showing you, that's a good example. It's not always perfect. Sometimes it misses radio bursts, particularly when they're saturated in the frame. But this is all just to demonstrate, basically, neural networks in machine learning and deep learning are able to process LOFAR data, recognize radioactivity in that data, and recognize the kind of radioactivity. This enables us to process large amounts of data on the fly, and also perform science of thousands, if not tens of thousands of radio bursts at the same time. So I'll conclude there and say LOFAR is an instrument. It's an instrument that can observe really fundamental plasma processes on the sun, from shock waves to particle acceleration. It can drive modeling, as I've shown. It's also a platform for big data science. So basically, not only can it do great plasma physics and observations of plasma physics, it can be used to do big data science with neural networks, deep learning, and a variety of other things if you have some nice high-performance computing facilities on its back end. And it provides a means of using and testing deep learning algorithms as well. So I'll leave it there. Thank you.